Yeah, so, all right, guys. Yeah, welcome to this lecture. This is going to be lecture 6, and I will tell you what this is going to be about. Now, this is going to be partially chapter 2 and also initiating chapter 3. So we're going to talk about the concept of stationarity, which is crucial in time series. Again, this is one of the most important concepts that there is. And later on in the lecture, I will basically teach you how to test it when you're looking at the time series, because again, you would need to decide. So this is where you start. You would need to establish stationarity, at least at the 5% level, or at non-stationarity, whatever. So it basically depending on what it would be. And then, yeah, you would need to work accordingly, because if a time series is non-stationary, that asymptotics, as you might learn in statistics, will not be true. Among others, the central limit theorem. Okay, so the normal distribution will not be basically the limiting distribution most of the time when it comes to specific test statistics. But I'm going to talk about that later on. Then I'm going to introduce basically two major processes that we're going to look at. White noises. White noises are stationary. Martingale difference sequences are not necessarily stationary. They can be. Again, I'm going to talk about also autoregressive processes in general, and of course specifically representation of autoregressive processes when it comes to basically, the structure of time. So that will be quite interesting. Basically, I will introduce two different types of representations. Each has basically its advantages and disadvantages depending on the assumption of time. And based on that, in the next lecture, which we're going to do next week, I will develop stationarity conditions basically for first-order autoregressive processes. And later on, during this course, I will generalize it for higher-order autoregressive processes as well. One autoregressive process that you saw is the one that you saw in the assignment, guys. And I want you to basically estimate parameters based on that one. But I gave you the sample, so actually you would need to know what to do. Now, anyways, I'm going to define stationarity here in the weak sense. There is also the strong sense. Strong sense stationarity involves distribution functions. But that's not a practical one. Okay, so again, it's relatively difficult basically to establish distribution functions, especially from data. And how would you estimate the distribution? So that question is not ambiguous, by the way. But again, so this is a very difficult concept. So therefore, I'm going to focus on the weak sense. Weak sense involves moments, okay? Expectation, variance, and autocovariance of a process. So let's say you have a stochastic process, which you denote by y. You can treat these things using random variables, by the way. So the process is called stationary if basically satisfies three of the major conditions. Number one, the expectation of a process, the unconditional expectation, is time independent and finite. If it says it's finite, then this basically means that if you calculate the expectation, you must have something specific. Okay, so that's basically condition number one. Again, keep in mind, guys, the unconditional expectation is always a constant if it's finite. Okay, whereas the conditional expectation is not necessarily a constant. It can be random, as you saw in the assignment, by the way. But this one is always going to be a constant. If finite, so if it's finite, that it is a constant, that's basically what it means. Okay, so a specific value cannot be infinite, by the way. And it must be time independent. I'm going to, again, so if you don't really sure how to deal with that stuff, I'm going to talk about that basically in detail in this course. So you see this next week, the week after, and so on. So again, this is one of the most important concepts there is. That must be also true for the variance. So the variance is also finite and time independent, by the way. And the autocovariance is also finite and it's also time independent. But it can be dependent on the time lag that is involved. So again, you might remember what the autocovariance is. This is the covariance of the process with itself, but a different point of time. Okay, so let's say most of the time you have a different point of time. So h is the time lag, which is not 0. If h is 0, then simply this degenerates to the variance. And I'm going to use basically gamma for denoting it. Okay, so you might not see this quite often, but in time series, if you talk about autocovariances, we are going to use basically gamma most of the time. Okay, in a multi-dimensional framework, you see capital gamma, which is looking like that. So this is basically always the covariance. But sometimes, again, so if you allow basically to for the time lag to be equal to 0, that also captures the variance as well. So I wouldn't basically, it would not be basically necessary to explicitly write down that the variance is also basically time independent, if that basically is allowed to do it here. But again, I'm going to split it anyway. So technically speaking, when it comes to stationarity, there is always going to be just two definitions, all right? So there are 2 points that basically would be required to be satisfied. number 1 and number 3, because again, if h is allowed to be 0, then the covariance or the autocovariance operator simply degenerates to the variance of a process. Is this understandable? All right, so that's basically what it would be. Now I'm going to just give you some idea how would that basically would be observed, okay, so when it comes to stationarity process. But before we do so, we're going to discuss some basic properties. Again, so you see, I mean, I'm going to show you a path of a, let's say, mean stationary process. There is mean stationarity and there is variance stationarity. Actually, for a process to be considered stationary, you need to have both. So you need to have basically the mean to be stationary and the variance to be stationary. What does that mean? This means basically that the mean is not depending on time. So when you look at the path, for example, of this process is clearly non-stationary, but at least the mean appears to be a constant. Again, so nobody knows what basically, I mean, you look at that data, let's say you have data observations related to the process. Nobody actually knows what the mean of the process would be, because keep in mind, and this is one common mistake, guys, the arithmetic mean of a sample is not equal to the expectation of a random variable that generates a sample in general. So you need to be understanding it. So again, when you have data like this, nobody knows what the expectation of the process, of the underlying process would be when it comes to the data. But let's say basically this is corresponding to this line here. Then you would clearly see that this line, okay, does not depend on time because, again, it's a constant, you know. So, I mean, it's a parallel to the x-axis, and x-axis basically time. So there is no trend in the data, let's say, even though the process evolves around a constant trend, you can say, but this is basically what it is. But the variance does not appear to be time dependent. So again, the variance is not, you know, is not these lines here, all right? So that's basically not what it is. But the variance of a process would be a measure representing the mean squared deviation of the process itself to its expectation, by the way. And that's something that appears to be time dependent because it might be subject to change. Again, so this just appears to be the case. Nobody knows what the theoretical mean and the variance of a time series is or are when it comes to basically these observations, but you should see that it appears to be the case that, you know, in this, let's say in this time frame, you have a different variance than in this time frame, which indicates that the variance will be time dependent. If the variance is time dependent, then the process cannot be stationary, by the way. So let's say, for example, stochastic volatility models, you might have heard of that, is a concept which, you know, we have time dependency of the variance basically, you know, most of the time, and depending on how the structure would look like. But it can be also conditionally time dependent. But I will discuss it later on. So most stochastic volatility models where you have time dependency of the variance. For example, this is typical for stock market returns, where if there is turbulence in the stock market, you know, then higher returns would also can be, or let's say higher volatility basically can be also associated with that. There is no such thing as volatility clustering, by the way. So this is how would you identify that empirically. Is it understandable? So at least what mean stationarity and what variance stationarity would be like. So again, for a process to be stationary, you would have both. And not just that, but, you know, you would have to have that the autocovariance is also not time dependent. But you could not see what the autocovariance of this process would be, unfortunately. You would need to use different diagrams, which I'm also going to show. Okay, so I'm basically focusing on mean stationarity and variance stationarity. Now, if you have a process which is variance stationary, okay, but not mean stationary, then it could look like this. So clearly, as you might basically guess, you know, there is a trend in the data. It can be a linear trend, but it's not necessarily the case. So let's say, you know, let's say a second degree function, whatever. It doesn't matter. So it could be a parabola, but sometimes it's not ambiguous. Okay, so you have, this is, let's say, the mean, and the mean appears to be depending on time, okay, because, you know, it involves a function that is time dependent clearly, okay, maybe a parabola, so second degree polynomial, stuff like that. Is it understandable? Okay, but the variance is not, because distance is related to the mean. Okay, so distances with respect to the mean appear to be constant. So let's say the length of this line is equal to that one and that one and that one, right? So indicating that the variance is non-time dependent, all right? Is it clear? All right, so that's basically what it would be. And for a stationary process, you have to have both. The mean is supposed to be time independent, as the variance is supposed to be time dependent. So again, but in this case, the variance is time, appears to be at least, you know, so appears to be because, let me remind you, nobody knows what, let's say, the variance of this process would be, okay? You would need to estimate it from the data. And that is also true for the mean, by the way. Okay, so even if basically time dependency, which is kind of exhibits that, then, you know, you would need to consider that one. Is this clear, guys? It's not necessarily a linear trend when it comes to basically, you know, the time dependency of the mean. Most of the time there is, okay? So just for the record, if there is some sort of dependency or some trend in the data, most of the time it's going to be a linear one because, you know, that's the easiest one, so it's always going to be the most common one. All right, guys, is it clear what stationarity could indicate in this sense? We're going to examine that from a theoretical perspective, so giving you, let's say, a first-order autoregressive process, and then you would need to establish stationarity of the process, both from the theoretical as well as from the empirical perspective. The empirical perspective is going to be a little bit more difficult, so we need to discuss the theoretical perspective first. All right, now let's say you have a stochastic process, and if it's stationary, then neither the autocovariance nor the autocorrelation is time dependent. Okay, so that's something that you would need to understand here, of course, by definition, right? Because stationarity means exactly that. Now, if this is basically the case, then you would have a different notation for the autocovariance and the autocorrelation. But it can be depending on the time lag. So let's say you have basically a time point, which is t1 here, and another time point, which is t2, this is here, and there is a time lag to both. So let's say this one is t1 plus h. Okay, so the distance between t1 and t plus h is h, of course. So this is the difference between them, you see? Okay, so t plus h is some point of time in the future if t1 is basically some point at the present point of time. Okay, that should be also obvious. And the same can be done basically for the time lag with respect to t2. So you have the distance between t2 and t2 plus h being also equal to h, right? So in this case, you have the same time distance between the two sampling points. Is it understood? Or let's say between the two sampling points respectively. So the time lag here is the same as here. Is it clear, guys? So that means that even if you have two different sampling points, the covariances with respect to the time lag for each must be identical if the process is stationary. So the covariance of the first sampling point with respect to the time lag h must be equal to the covariance with respect to the second sampling point and also with respect to the second time lag h. All right, so is it clear? So this means that, of course, the covariance is time independent, but keep in mind that it could be depending on the time lag, because technically speaking, the greater the time lag, the less impact of a corresponding observation would have on, let's say, another observation, which is, let's say, some observation point in the future, okay? So again, stock price, let's say, if we talk about stock prices, and if, let's say, there is some sort of autoregressive relationship between stock prices, stock price of today would rather depend on the stock price yesterday than on the stock price, let's say, 30 years ago. You understand what I'm saying? So if your time lag becomes large, the covariances tend to become basically small. You understand what I'm saying? It's not necessarily zero, okay? So that can be still have, you know, if the process is autoregressive, let's say, then stock price of 30 years ago could still have an impact on the current stock price, but empirically speaking, that impact is rather less, okay? So make it basically rather small than if there is, you know, a shorter time frame or let's say a shorter time lag to it. Is it understandable, guys? So that must be considered. Okay, so there is a time dependency regarding the time lag in general, even though the process is stationary, but not at the sampling point. So all that matters is basically the time lag between two sampling points, but not the sampling point itself, so where you are. Okay, but basically how far you go to the next one. And in that regard, if there is no time dependency involved, okay, then we write basically for the autocovariance a different expression. So we simply just write that it would depend on the time lag only, but not at the sampling point, t. You understand what I'm saying? So this is basically used for stationary processes only. So if the process is stationary, I will drop t from the autocovariance operator and simply just use h, because it would not depend on the sampling point, t, which is either t1 or t2 here. In this case, all right, all that matters is the time lag, and the same is true also for the correlation as well. Okay, so if the autocovariance does not depend on the sampling point And if the variances don't depend on the sampling points either, then of course the autocorrelation does not depend on it either. So when it comes to stationary processes, let's say if y is stationary, then I will simply just drop t from the covariance, autocovariance as well as the autocorrelation operators, and I'm simply just going to use h with reference to the time lag. You understand what I'm saying, guys? Of course, you need to have some sort of sampling points, but you can do it anywhere. It doesn't really matter. All that matters is the time distance between the two, but not basically at which point are you measuring it. Is this understandable? Because it doesn't change by time. That's what stationarity requires. You got that? Okay. So again, this is very important. Now, there is also another property. So if the process is stationary, then of course you also have that looking into the future is going to be the same as looking into the past. All that matters is just a time distance, but not the direction related to time. So this is what I call invariance of the time shift. Okay, so invariance of the time shift means just that. Okay, again, so this is, I'm not sure you can Google it, but you probably get something else. But I call it the invariance of the time shift. It doesn't matter whether you look into the future or into the past. All that matters is basically the time distance between two sampling points when it comes to a stationary process, or basically when it comes to the autocovariance of a stationary process. Okay, so what I mean by that is this, basically. So the autocovariance between t and t plus h, which basically reference to that one, is going to be the same as the autocovariance between t and t minus h. So let's say h is basically greater than 0 in general, then this would be basically mean that the autocovariance between these two, or with respect to these two sampling points, would be just as equal as these two, okay? So even if that regard, so when it comes to autocovariances of stationary processes, usually I will use that h is going to be greater than 0 without loss of generality. So when it comes to a stationary process, you can simply just use, and this is what the statement would be about, h to be equal to 0 without loss of generality, so without loss of generality, okay, so that's basically what it would be, okay, ohne Beschränkung der Allgemeinheit, maybe you know that term, okay, so when it comes to stationary processes, I only look at basically the time lag, which is greater than 0, because I know that the autocovariance with respect to the time lag plus h is going to be equal to the autocovariance with respect to the time lag minus h. In order to be able to do so, to show that to you, but you need to understand that the equalities here are not true for non-stationary processes in general. So if the process is non-stationary, these equalities are not necessarily true. They can be true, but not necessary, all right? Okay, because you would have time dependency with respect to the autocovariance in general. So it would depend on basically the sampling point. If it depends on the sampling point, then it's also basically depending on the time shift with respect to that sampling point, because that might be subject to change, but it's not necessarily the case though, all right? Again, keep in mind you have to satisfy 3 conditions, not just 1, but 3, all right? So that's basically what I want to emphasize here. But if the process is stationary, these things are true. Now let me show that to you. So we're going to look at that one. It's not difficult, by the way. So we look at the correlation because, that's quite straightforward. The correlation of a stationary process with respect to basically to time point t and time point t minus h would be, first off, the autocovariance of the process at time point t and with respect to time point t minus h divided by the standard deviation at time point t multiplied by this in the denominator multiplied by the standard deviation at time point t minus h. Now, first off, you need to know that the covariance or the autocovariance operator is a symmetric one. So you can basically just interchange. So that's what I do. I'm going to basically put the last one to be the first expression, and as well as basically the first one to be the last one. So covariance of x and y is equal to the covariance of y and x, because this operator is a symmetrical one. Okay, so that operator is symmetric. So since this operator is symmetric, you simply just interchange that. And I can do that basically for the variances too, because multiplication is commutative, guys. A times b is the same as b times e. A times b is the same as b times a. So that's why basically I would change that. I do this for practical reasons, because later on I could substitute t for t minus h. Now why? Why I'm allowed to do this? Because the process is not stationary. If a process is not stationary, then I could change basically the time point when it comes to these moments. Okay, so that is basically both true for expectations, variances, and autocovariances, because keep in mind, you can use basically for all moments, actually. You know, variances are also referring to some moments that are involved. You know, you have the second moment in there and the first one also, and the same is true for basically for autocovariances as well. So I could basically change at, you know, the time point as I like. Okay, so there is no limits basically with that, because if there was an issue with that, then the process would not be stationary. So since I'm allowed to do this, I would basically substitute basically t for t minus h when it comes to the first expression. If you do that, this is what you're going to get. All right, so you can basically t plus h, actually it's what it is, it's not t minus h. There is an error on the slide, but unfortunately, so you would not, I mean, I didn't see it first, but when it comes to editing, of course, what I did is basically substituting not t for t minus h, but t for t plus h. I will fix that one. Okay, but the result is correct, so just a comment is wrong, but it doesn't really matter. So t, as you see, becomes t plus h, and this concept is just simply, you know, used as consequentially. I apologize, I remember me doing that t minus h, but anyway, so because first I was, you know, calculating the autocorrelation with respect to time lag plus h, not minus 1. But anyways, so the result is still correct, although the comment was just wrong. But you can basically substitute with anything you like to, it doesn't really matter. Now, if you continue, guys, okay, which I'm going to, you can just clean up. Now, there is expressions that are equal, okay, so that doesn't change, of course. That doesn't change either, okay, so the only thing that would change is basically t plus h minus h, which of course yields to t, okay, so that is obvious. And then here the time index says t plus h minus h, which is also equal to t. And what you see here is basically, you know, you can see that the autocovariance of the process with respect to the time lag plus h, and then you would divide it by the product of the standard deviations of course of time. So this is basically clearly the autocorrelation, or I mean the autocorrelation with respect to the time lag plus h. So I was showing that basically these two are simply just equal, although the comment was wrong. Anyways, is it clear, guys? So that's what you would need to understand here. Now, again, this as a consequence, when it comes to autocorrelations or when it comes to autocovariances, I will simply look at the case where h is greater than 0 only. This allows me to basically to skip, you know, certain cases, all right? Because I know that that will be also consequential true when it comes to the time lag minus h. So I will use that one only when it comes to stationary processes, all right? So only these cases. I will go basically into the, I will look into the future, no longer into the past, you know, when it comes to that one. Anyways, guys, okay, so that's something that again, you will see quite often. Anyways, so if the process is stationary, then you would also know that the expectation is finite, the variance is finite, and the autocurrences are finite, and they are also time independent. Now, I will extend this concept because there is also a weaker form of stationarity when it comes to that. So there is also asymptotic stationarity. Asymptotic stationarity simply means stationarity in the long run. So that means that basically the expectation, the variance, and the autocovariance might be time dependent, okay? So this allows it to be, so these moments, let's call them moments, okay? Although they're not, but I will call them moments, okay? So that's simple. These moments to be time dependent, but actually in the long run, they're not supposed to be. So their limits, okay, don't depend on time anymore. So when you calculate basically the limits, where the time converges to 0, you'll find that the expressions coming out, again, so these limits must exist, of course, right? So they must be finite, okay, which is straightforward. So when you look at limits, you know, they must be there, okay? So it's not supposed to converge to infinity because that would mean that it would diverge, okay? And it must be basically time independent then, all right? So in this case, you know, at least the limits must be basically time independent. Each expression can be time dependent, guys, okay? So you have basically t involved when you calculate the expectations, but in the long run, that should not be the case. So this is what the interpretation would be. Stationarity, okay, asymptotic case, is going to be stationarity in the long run. If a process is stationary, then it's also going to be asymptotic stationary. That's obvious, right? So, because if it's stationary at all points of time, then it's going to be also stationary in the long run. You understand what I'm saying? But it's not going to be, the opposite is not going to be true. Okay, so just because it's asymptotically stationary, it doesn't necessarily mean that it's going to be stationary, strictly speaking, although it's going to be both referring to the weak sense, all right? So that's something that must be true, again, and if basically, let me summarize this, if a process, these two things I just mentioned, if a process is stationary, then it's going to be also asymptotically stationary, that's normal, okay? So when it if the moments are time independent, then of course the limits are also time independent, okay? Because, I mean, why would you calculate the limit of something if there is no involvement here? So that's going to be the same. And asymptotic stationarity can be interpreted, as I mentioned before, as stationarity in the long run. So I simply say it's going to be stationary in the long run. It might be subject to change regarding the mean and the variance, for example, right now, maybe in a short time frame, but in the long run, it's not going to be affected by it, which is typical also, by the way. So you can basically have that point as well, both from empirical as from the theoretical perspective. Okay, so stationarity in the long run, this is my interpretation regarding asymptotic stationarity. Is it clear, guys, what it means? Okay, so you could have basically, let's say, a current point of time. There might be some turbulences regarding, you know, the variance, for example. Variance can be time dependent in that regard, but in the long run, it will not be. Okay, that's what it means. Is it clear? All right. So, for example, seasonal data, you know, will be stationary in the long run. Actually, you know, I mean, you know, if there is no linear trend. But anyways, okay, so that's that. Now, I'm going to introduce another very important process, which is the white noise. The white noise process is, again, is an important one, is a process which has zero mean, a constant variance, and zero autocovariance. That's simply it. So the expectation of the process is zero at all points in time. The variance of that is going to be a constant. It's not necessarily normal, guys. So again, I have the experience that people tend to associate mu and sigma with the normal distribution. That's not true, okay? So again, this is just simply mean that you have a constant variance, okay, which means that it's not time dependent, by the way. So that might be indicating that already that the white noise process is going to be a stationary process, which it is. If its autocovariances are going to be basically zero. So again, this is what I mentioned before. The autocovariances are zero, of course, if h is not equal to zero. Technically, you can also replace that by saying that h is greater than zero, because I mentioned before, you don't need to look into the past. Okay, when it comes to the autocovariance, you can simply just use basically h to be positive without loss of generality in that case. But I will keep it as is, so it would not bother me. But anyway, so that's that. You understand? So in this regard, this is the first stationary process that you're going to see, and that is what I'm going to use basically to assume the noises when it comes to some sort of linear relationships between a response and some predictors. Okay, so that's basically the general model that I will use. I will add some noise, and I'm going to assume that it's going to be a white noise, which means that it's going to be a stationary noise around zero. So it means zero, of course. All right. So again, I mentioned before, since the expectation, the variance, and the autocovariances are not time dependent and are finite, of course. So of course, zero is finite. That is true. Sigma squared also. And that is, this expression is also finite and time independent, right? That this means that the noise is going to be stationary. And that is going to be a standard assumption, by the way. Okay? Further properties of the noise include the following. Again, you might be doing that as well. For example, when it comes to regression models, I usually assume that the conditional expectation of the noise given the predictors is going to be equal to zero. And of course, its conditional variance is going to be, let's say, at least a positive definite matrix, by the way. But that's something we don't discuss now because this is an assumption that I used in the second assignment. So that's basically what the second assignment was about. Okay, so what is, I think, to be spectacular, just to be honest, so let's talk about that a moment. Okay, if I assume, for example, that the conditional variance of the noise given the predictors is going to be zero, and also the conditional variance of the noise given the predictors is, let's say, going to be some constant, then this implies, among others, that the noise is not correlated with the predictors, okay? And I basically find this very fascinating, by the way, okay? So, but to be honest, again, this can be done directly, and this is something that you have already submitted, guys. But I wanted you to go through these steps. So just based on these two assumptions, which are relatively weak, by the way, weak assumptions are in that regard very practical because they are easy to be justified. Okay, so how would you justify this assumption? And so if it's a weak one, then it's easy to do so. Okay, so the weaker assumption is, the easier it becomes to be justifiable, right? And this implies a lot of things, you know. So, and that's what you have already discussed, by the way, very successfully. I wanted to mention. Okay, so in general. So, but that's that. Okay, well, I'm not going to basically start off from here. I'm simply just going to assume that the expectation of the noise is going to be 0 and the variance of the noise is going to be constant, because this can be easily justified if I assume that the conditional mean and the conditional variance are in given some predictors most of the time, and there are some linear predictors that are involved in the linear models, you know, are the way that I was basically illustrating in assignment 2. Okay, so but I'm going to start here. I'm not going to start from the conditional expectations. But anyway, so that's that. Now, the white noise process could be, I mean, I generate a sample. It looks like this, or a path, to be honest. So let's say this is how it would look like. You're not seeing it, by the way, directly, that the variance is constant, but, you know, the mean at least, you know, appears to be basically evolving around 0, which is, you know, I think obvious, more or less. But again, nobody knows what the theoretical expectation of the process will be, but it appears to be basically 0. It's at least, it appears to be consistent with the assumption that the expectation of the noise is 0, and the variance is going to be basically also a constant. In this case, it's 1. Again, so this is not telling you that these lines are basically hidden there. Okay, so you cannot see from the diagram it's actually what the theoretical or even the empirical standard deviation of the process would be. All right, but I just use it as an example here. So I was giving the process these parameters, and basically my computer was generating a sample from it. Okay, and that would be considered to be, let's say, a noise, and this is how it would look like. So that's actually how a typical stationary process would be. Okay, so you have some sort of, again, so it could be looking like that, right? So if you have basically increased the frequency, this is what it would look like. And especially when it comes to the noise, this evolves around 0, and then you would have the variance, which appears to be also time independent. So that's how, typically speaking, a stationary process would look like from the empirical perspective in general. Is it clear, guys? Okay, so which is consistent by the noise, with the noise actually. So yeah, all right. Now next we're going to discuss also properties. So again, keep in mind, guys, the noise is stationary. Okay. And as well as asymptotically, okay? So in both cases, so typically stationary, but also asymptotically stationary, because any process is a stationary process is also an asymptotically stationary process, by the way, and serially uncorrelated. Why? Because the autocorrelences are 0, but not necessarily independent, guys. So just basically, you know, make sure that the two things are not basically don't imply each other in general. It's serially uncorrelated. Okay, there is no linear relationship of the noise to its path, but it can be basically a dependency which is going to be different. Now, most of the time, to be eliminating that, we assume that the noises are normal. If you assume that the noises are normal, then it's going to be both. It's going to be serially uncorrelated as well as serially independent, because as you might know, if basically two normal random variables are uncorrelated, then they're also going to be independent as well. Again, I was demonstrating that using the densities. You might remember that. So for the normal distribution, this is becoming equivalent, by the way. If normally distributed random variables are uncorrelated, then basically they're independent, because linear relationship can be the only relationship that you can establish when it comes to normal distributions. Okay, I've basically demonstrated that using the correlation parameter. Anyways. So, but it is, if it is serially independent, which is the case if the noise is normal, so we assume that most of the time the noise will be following the normal distribution. Why would we assume anything else? It's practical, by the way, and it's not difficult to justify it. Okay, we simply just write that the noise is IID, by the way. Okay, so you have seen this notation. I just wanted to basically put that in the context of time series. Okay, the noise has basically the mean 0, and it has a constant variance, and that's that. But the mean is always 0, guys. Keep that in mind, okay? That's important. Is it clear? All right, so this is basically how we'll deal with the noise. Again, I use basically that notation most of the time. Okay, and we are assuming that it's IID. That can be basically achieved if the noise is serially uncorrelated and normal. And it's also IID, by the way. Okay, so if basically the noise is normal, okay, so normally and independently distributed, then of course, you know, I mean, or identically distributed. So if it's normal, then it's also going to be IID. All right, so that's something that you would need to basically to grasp with the same parameters, of course. Okay, that's why, among others, the normality of the noise is so popular when it comes to that. All right. Now, anyways, yeah. So we are going to continue. A process is called MDS. I say MDS most of the time. Martingale difference sequence. If it satisfies two conditions. The expectation of the absolute value, and you know how to calculate this, by the way, so you did this in the first assignment, so you basically can imagine what to do, is finite. So if it's finite, then this guarantees, by the way, that the variance of the process is also finite. So the issue is, you know, you need to make sure, if that's the case, which, again, it might be abstract, but you did this in the first assignment. This implies, among others, that the expectation is finite. Okay, so the expectation is finite, as well as the variance is finite. So basically both are finite. Okay, so that's why, you know, that combines the two. Okay, I'm not going to discuss it. This is called also absolute summability, basically, by the way. And since that is going to be square summable at the same point of time, then the variance is going to be finite as well. Anyways, okay, so that's what it is. That making sure that the moments are finite. Excuse me. You got some? Excuse me. Excuse me, guys. You got some questions?
About the notation, but it's fine.
Yeah, yeah. Which one? Which one? IID?
About the one that it's now on the slide, but I understand.
Which one? So the IID what? Or
No, the one with...
on this slide? So which...
Yeah.
MDS? Okay. So expectation of the absolute value must be finite. This means it's finite. Okay. So that maybe you have seen this before.
Yeah, it means that basically this phenomena, right, it goes to the...
It's a constant.
Yes, constant.
That's it. It's a specific constant. Okay, that's it.
Yeah,
so you have sometimes when you calculate, for example, these integrals, all right? Because that involves basically what the expectation is. Integrals are limits. Okay, you understand what I'm saying? Limits of sums. And these limits can be also divergent, okay, which non-existent, by the way. So this means that, you know, if this is finite, you know, then you have a finite expectation. Okay, now in this case, not just that, but also if you, let's say, take the absolute summability concept here. Okay, that's what it means. So keep in mind, expectations are also limits when it comes to continuous functions or continuous random variables that are involved. Okay, I mean, especially when it comes to processes. So from the application, or from a perspective of the application, you can treat processes to be random variables, you know, when you calculate moments, expectations, variance, and so on. Okay? And keep in mind, if there is a density function, then expectations are going to be limits. Okay? And that limit must exist. That's what it basically what it means. And that must be also existent here for that one. Okay? So that's basically what the notation is about. Again, I thought that basically would be obvious, but that's means it's finite, okay, less than infinity, okay. I mean, if it's equal to infinity, then it's divergent, right? So that would be the other case. So limits are either divergent or convergent, let's say, okay. So if you have a limit, okay, so that's either equal to infinity or it's less, okay. And if it's less, then it's simply convergent, okay. So because there is always a sequence involved. Anyways, the other one is Yes, sure. But if it's not specific, then it doesn't matter whether positive or negative. So it's actually plus minus infinity. But if it's, you know, you don't write it's less than minus infinity because it doesn't work. So if it's basically, it's not infinite. Okay, so it's either basically somewhere specifically. It's a constant, you can say that. All right, so that's it. And a constant cannot be infinity. Okay, because I was criticizing that, by the way. You know, especially when it comes to integrals, right? You could not write e to the power of minus infinity or something, even though it works, you know, but unfortunately minus infinity is not a real number, so Yeah, and I would need to basically, cut off at least 1 or 2 percentage points. Anyways, because it's not mathematically, formally speaking, it's not perfect, so. But anyways, now the second property which it has is that it's conditional expectation, and at time point t, of course, with respect to its past. Okay, so when it comes to see that, because you see multiple ones, all right, and basically it's going to be 0. So this notation means the total past of the process. Usually this is expressed by using filtrations. I don't want to introduce the concept of filtrations, especially not for discrete time stochastic processes, which is, not ambiguous, so it's not very straightforward to consider that one. But when it comes to application, guys, you need to calculate. This means that anything which relates to its past can be taken out from this expectation operator. Okay, so especially when it comes to, let's say, autoregressive processes. I will give you an example, and that basically might answer your question, how to deal with these things, because this is basically what the last assignment was about. Now, I'm going to show that if a process is an MDS process, so let me refer to that as MDS again, Martingale difference sequence. If it's MDS, then its unconditional expectation will be 0. That's number 1. And it's going to be serially uncorrelated. Okay, so the autocorrelations are going to be basically 0 as well. I'm going to address both. Okay, but you need to understand before I continue, the MDS process is not necessarily a stationary one, because it can be the case that the variance is time dependent. So keep in mind, guys, there is no basically restrictions involved when it comes to the variance of the process, and that's something that you would need to understand. All right, so a MDS process can be also instationary, but it allows us, and one of the most important types, okay, so sometimes we simply just assume that the noise is MDS, so at least evolves around 0, and at least it's basically serially uncorrelated, but it can be having a time-dependent variance, which we're going to discuss. And one example related to that is going to be the so-called arch-gauge processes. I'm not sure if you heard about those. Arch means autoregressive conditional heteroscedasticity. Okay, conditional heteroscedasticity means that the conditional variance is time-dependent, and it's autoregressive, so it's linear depending on its past, but it can be stationary. So although the conditional variance is time-dependent, arch processes are going to be stationary, or sometimes not, but against some specific, restrictions. So when it comes to constraints, you can establish stationarity under certain circumstance, even though the conditional variances are going to be time-dependent. That appears to be contradictory, by the way. So how come basically the unconditional variance is not time-dependent when the conditional variance is? But we're going to answer that question later on. This is a very, very popular class of processes, and you would need to understand them. So I'm going to talk about them also. Anyways, so when it comes to basically these MDS processes, again, you need to know that the conditional expectations given its past is going to be 0 all the time. So, and I'm simply just applying the law of iterated expectations, as you see how it works. The unconditional expectation, according to the law of iterated expectations, is always going to be equal to the expectation of the conditional expectation. And I simply use basically the conditional expectation with respect to the past. So you don't need to basically specify what the conditionals are. If I'd say basically given the total past, the expectation of the conditional expectation of the process is going to be equal to its unconditional expectation. This is a very, very powerful tool, by the way. So you're going to see this in econometrics, you're going to see this in time series, you're going to see a lot of things. So this is basically the bread and butter when it comes to calculating unconditional expectations, okay? Because most of the time, conditional expectations involve much weaker concepts, by the way, and you can simply just generalize them looking at like this, when we're looking at this basically right there. Now, the conditional expectation is 0, so since basically the conditional expectation is 0, then this means that the expectation of 0 will also be equal to 0, and that implies that the unconditional expectation is also going to be 0, by the way. Okay, so that's that. Now, when it comes to the autocovariance is, of course, equal to the mean of the products minus the product of the means. All right, so that's basically that. Of course, with respect to time, like it's time point t and time point t plus h, So when it comes to that, again, keep in mind, MDS is not necessarily stationary, but the unconditional expectations are 0. So I simply just use that. And again, I'm going to use the law of iterated expectations again, because the expectation against the unconditional expectation, how to do that is going to be the expectation of the conditional expectation of the products. And I'm going to be, very, very straightforward here. You can use any past. So if you have basically the time point t plus h, and I assume that h is greater than 0 without loss of generality, you find that this is going to be, and this is what you'll have here, the expectation of the conditional expectation of the product of the two given the past. Now the past starts already at time point t this time, because let's say you would consider time point t plus h, and if h is basically greater than 0, then the past also includes already the observations at time point t minus 1, and so on. Now here basically comes the answer to the question. If you have these, as conditions, okay, but actually one would be enough. This means, okay, so if you find it here in the condition, this means when it comes to applying it, you can take that out from the expectation operator. This is why it's so practical, okay, and that's what I'm going to do. So you have that basically here, and this is what I did. So the expectation of yt times the conditional expectation of that, and that is equal to 0. So since basically this is equal to 0, the expectation of yt times 0 is also equal to 0. And that means that, of course, the autocorrelances are also going to be 0. So that's that. Okay, simple as. Again, so the law of iterated expectations is a very, very powerful tool when it comes to calculating these things. And I would basically recommend you considering them. And yeah, that's it. Okay, so two major properties, all right, of the MDS. Number one, expectation is 0. Number two, it's serially uncorrelated, right? As you see, obviously, Well, now when it comes to the variance, that can be different. But, and again, so inside you can see this here. If t is equal to 0, then you cannot basically put the current observation as into the condition operator because it doesn't work, okay? So given the current point of time, the current observation is not given. This is not basically what an MDS is. The expectation of a current observation given its past. So you have to have some basically time points before that, not at the same time point. Okay, so that would not work. So this calculation only works, and I forgot to mention this, it only works if h is greater than 0. You understand what I'm saying? That's it. Because if it's equal to 0, then it doesn't work. Okay, so you cannot use that basically addressing the variance of the process by that. Okay, because only it means expectation of a current observation given the past is 0. Okay, that's what it is. Now, and so therefore h must be greater than 0 then. All right, now we're going to discuss autoregressive processes, and I have basically mentioned before what the first order autoregressive process was. In the last assignment, or when I was introducing you to the last assignment, this is how it would look like. Okay, now I use capital letters basically illustrating that as random variables, and I'm going to address the noise as well. So let's say the noise is, let's say IID without loss of generality, but nobody cares actually. So you have basically 2 parameters, actually 3, because the variance of the noise is also part of the parameter space. But again, when it comes to the process directly, so let's call them the direct parameters that are directly, specifying the autoregressive process. It might be the case that the noise have a different structure other than basically the white noise, but I assume it's going to be a white noise this time. So if it's a white noise, then it has a variance sigma squared. So sigma squared, again, is also usually part of the parameter space, but again, I will not address it as such. If you have an autoregressive process, the notation is going to look like this. And if it's a first order autoregressive process, you simply just put in 1 in there. How would you recognize it's a first order autoregressive process? Because it only depends on its past observation on a time at a time point which is just 1 step away at the current time point. So if let's say the current time point is t, then and you have daily observations, then the time point at t minus 1 would be the observation yesterday. So the current observation of today would linearly depend on the observation yesterday. So when basically the frequency, you have daily data, okay, and then plus some noise that kind of disturbs that. And if you have a process like this, then it's going to be an autoregressive process. I'm going to discuss basically properties of autoregressive processes in next week's sessions. Okay, so I'm not going to do that now. Okay, how would it look like and how would you recognize and blah blah blah, because it kind of involves some things. Today we're going to focus on representations of first order autoregressive processes only. So there is a different way basically to represent them. This is the recursive representation. So that representation is called recursive. Okay, and yeah, because it you have the current observation and the past, and there is just one step basically where you have a direct impact. The others are indirectly there also, because on the other hand, the past observation would also depend on a previous observation to another past. So yt minus 1 would be equal to, let's say, the constant, which is v plus a times at time point yt minus 2 plus epsilon t. So again, this indicates that the current observation would also depend on that one, okay, because you would go back 2 steps, but not directly. So it doesn't depend on directly, only through this, let's say, this observation here at time point t minus 1. So there is no direct impact of this observation anymore at the current observation at time point t then. Is it clear? All right? But there is also an indirect impact on that. Anyways, we're going to discuss it further. Okay, so that's what it is. Now, if you have a second order autoregressive process, then you have a direct impact of that one as well. So I call basically these parameters A1 and A2, which are involved, okay, instead of just A. And you can go back 2 steps in time if you have a second order autoregressive process. This is also linear structure. So in this case, you have, technically speaking, you have 3 predictors, but actually 2 exponential variables. So the current observation directly, not just indirectly, the current observation at time point t depends on the observation at time point t minus 1 and the observation at time point t minus 2 directly. And that's basically the linear combination of those would generate the new observation at time point t then, plus a noise at time point t. And this is basically how it evolves. All right? Is it clear, more or less? So let's say intuitively speaking. Okay, in this case, you simply just write that this is an AR2 process. AR stands for autoregressive. Auto means basically with itself. So it depends on past observations of itself. Basically, current observation. This is basically what is called autoregressive. And AR2 processes, again, will give you basically how far you can go back in time when it comes to direct impacts of past observations on the current observation of the process. Sometimes I use basically the noises to refer to them as shocks. Okay, so sometimes I would say a shock at time point t. Okay, so from the context, because it can be interpreted as such, but that's just an interpretation. Anyways, of course, you can basically extend this for even higher orders when it comes to that. Typically speaking, the order is very, very high. So when it comes to, let's say, for example, daily observations, okay, that's typically, I mean, stock market returns and stuff like that. But I'm going to basically give you the idea how to address those processes when it comes to basically higher order autoregressive process, because on the other hand, if the number of parameters that are involved here is relatively large, then how would you basically estimate a large model like that from, you need to have basically a lot of observations to do so, which is not very practical, by the way. There is an issue how to overcome this. So when it comes to, simplifications, but I'm going to discuss this during lecture. Now, in this case, you write that this is an ARP process. AR means autoregressive, and P is the order. Of course, P is an integer, right? So that must be some, let's say, element of the set of natural numbers, which I didn't declare, but it should be obvious at this point. All right, so time distance, equidistant sampling points without loss of generality. Okay, so you always have equidistant sampling points, even if the weekends are off. Okay, so weekends, stock markets are closed on the weekends, but it doesn't matter. So, there is maybe from Friday to Monday, there is just one day basically distance, because Saturday and Sunday stock markets are closed. You understand? So it doesn't matter. Okay, so you always have equidistance when it comes to equidistant sampling. And yeah, so time point t minus 1, t minus 2, t minus 3, and so on, and t minus p. So there is still a direct impact. So this is the linear structure. Okay, there are p plus 1 predictors actually, which means that there are p exponential variables when it comes to the current observation. And yeah, this is how it will look like. Now, I'm going to focus on the first order autoregressive process, but basically I will discuss some major properties that higher order autoregressive processes also have. Okay, first is that there is no correlation of the current observation of the noise with the past observations of the process. I want to demonstrate this. So the current observation of the noise, again, so the noise does correlate with the past, but only past observations of the noise do, not necessarily current observations do. Okay, so the current observation, I mean at time point t. So the noise at time point t does not correlate with the past of the process. So if basically h is going to be greater than 0, this is the past of the process because the noise is a white noise. Okay, so again, if there was, that would indicate that the noise is not serially uncorrelated, which it is. Okay, so that would contradict the definition because past observations of the process y would also include past observations of the noise. So if there was basically correlation between the current observation of the noise and the past of the process, this would indicate that the noise would not be serially uncorrelated, but it is in contradiction by definition. Because if I say noise, I mean always white noise. Okay, so you have a white noise involved here without loss of generality. All right, is that clear? Okay, so that's property number 1. This is also true for higher order processes, whatever you have, but there is correlation of the current observation of the noise with the current observation of the process. Keep in mind that the current observation of the process directly depends on, I mean, there is no observation of the noise in general because the noise is not observable. So if I say observation, I just mean basically hypothetically speaking. So hypothetically speaking, okay, the noise is not observable in practice, but if it was, it directly impacts basically the process itself at time point t. So this means that there is a correlation between the two. So the current observation of the noise, so the observation of the noise at the current point of time would correlate with the current observation of the process, also theoretically speaking. If you want to see this, it's relatively easy to do so. Okay, so this is what the autoregressive process would be. Now, I was giving you a statement in the previous assignments though, or basically I was mentioning that if basically processes are serially, or not serially, sorry, if processes are pairwisely uncorrelated, so let's say you have two random variables, x and y are pairwisely uncorrelated, and also x and z are pairwisely uncorrelated. And not just that, but you also have that y and z are also pairwisely uncorrelated, then the covariance of that is just going to be the variance of the random variable that both have in common. You can say that this is the intersection, basically, of the two. Okay, so the covariance of sums, if the summands are pairwisely uncorrelated in general, then this is going to be simply the variance of the intersection of the two sums. If I say intersection, I mean those summands that they basically overlap with each other. Okay, so again, if basically x, y, and z are pairwisely uncorrelated. Okay, so pairwisely uncorrelated. Okay, so if this is basically the case. So x and y are uncorrelated, y and z are also uncorrelated, and x and z are also correlated in this case. Now, this allows me basically to consider only those types, okay, when it comes to a sum. So you keep in mind, guys, this is a sum, this is basically the first part, and that is going to be the second part, okay? And only the blue parts basically overlap because the yellow one and the blue one does not. Okay, so the yellow one is uncorrelated with the blue one. You understand what I'm saying? If this is basically true, then you simply just take it out. Okay, you can simply just dismiss it, by the way. Or you can directly write that this is just going to be the variance of the noise. And the variance of the noise is a constant by definition. But since basically this is greater than 0, there is correlation of the current observation of the noise, hypothetically speaking, with the current observation of the process. Okay, so that's something that I want you to remind you. All right? Is it clear, guys? All right, so this is important. And yeah, so again, no correlation of the noise with the past observation of the process, but with the current observation of the process, there is a correlation with the noise. Because, of course, the noise directly, you know, has an impact on the current observation. The current noise has a current observation of the process. All right? Is that clear? So there is correlation between the two. Yeah, you got a question.
That as well, for example, instead of one of these independent variables we replaced with another. I mean, with, for example, if y t minus 2 be replaced by x.
Yeah.
Is the same?
I'm not sure if you understand the question, but yeah, so that would be basically, you know, you have that in here. So for the covariance, I write it like this. So let's say you have a covariance of x, okay? And then you have, let's say, y plus x inside, right? Okay? So, and if you see something like that, okay, then this is going to be equal to the variance of x, which it is true, provided that basically that x and y are uncorrelated, okay? Okay, so that's what your question was about, which is true, by the way, because the current observation of the noise does not correlate with the past of the process. So there is no correlation basically between the blue part, again, so this is the blue part, and the yellow part, which was the implication prior. So that's the second implication, but that was the implication prior. Yes. So if that resembles basically, I think if I understand it correctly, that resembles basically a comment. All right, is it clear? All right, so that's basically what I wanted to mention here. All right, guys, so that's basically what it is. Now, I'm going to discuss some representations of the first order autoregressive processes. Now, you will see, and this is going to be very interesting, to be honest, the representation will depend on time. So basically, you will need to have assumptions related to time. This means that how far can you go backwards into the past, okay? And that depends on the structure of time. So it's quite interesting concept, by the way. Okay, so the structure of time, you know, so it's an abstract one. It's also a metaphysical one, as I mentioned before. But again, so it's not going to be uninteresting. Anyways, so how would you basically consider that? Keep in mind that the process at time point t minus 1 is going to be the linear transformation of the process at time point t minus 2 plus the noise at time point t minus 1. That's something that you would need to do. Okay, so simply replace, if you substitute t for t minus 1, you're going to get basically this equation in red, as you see. Now, what I can do is, of course, I will substitute yt for yt minus 1. So that one basically goes here. Okay, I take that and put it in here. Okay, so that's going to be basically the first step. And I'm going to use the multiplication to get those 8 times v is simply 8 times v, as you see. 8 times yt minus 2 is a squared times yt minus 2. And then you have 8 times the noise at time point t minus 1 is 8 times the noise at time point t minus 1. Okay, so this is simply elementary calculus. If you take that, so summarizing it, because this is basically what the first iteration would be, I will collect those. So this is going to be v times 1 plus a in brackets, of course. Then you have a squared times yt minus 2. And then you have the noises, which I'm going to restructure. So I'm going to put the noise at time point t first. And then you have basically 8 times epsilon at time point t minus 1. So this is going to be the first iteration here of the process. You might ask yourself, why am I doing that? But I'm going to come back to that issue later. You don't need to know this, but this is basically simply substituting basically for yt minus 1 for what it is. Okay, so that's what basically how would it generate it from. And now I would continue from here, and I could also substitute for yt minus 2, because keep in mind, guys, yt minus 2 is equal to, and this is what you will see here, to the linear transformation of the observation yt minus 3 accordingly, plus the noise at time point t minus 2. Is it clear? And now you're going to substitute that yt minus 2 for basically what it is. Okay, so I'm going to put that back in. And if you do, you just simply need to multiply, and if you see that correctly, you simply need to multiply the yellow frame by a squared. Okay, and then you would get back basically those expressions that are still missing. So I'm keeping those that are already there, and I'm going to, you know, put in those expressions that are missing here from it. So if you do that, which I prepared, so this is what it would be, you get basically a squared times a constant, which I'm going to simply put it in here, you see. So 8 times the constant is going to be here. Okay, so v times a squared inside. So, and the expressions which are there are already there. so don't need to look at that anymore. Then you have basically a squared times a times yt minus 3 yields a cubed times yt minus 3, all right? And then you have finally a squared times the noise at time point t minus 2 equals a squared times the noise at time point t minus 2. Okay, so simply just basically add to the consideration. And this is how it evolves when it comes to these iterations. I'm going to do another one, so you see it there basically, and then I'm going to generalize it. Keep in mind, I also can substitute for yt minus 3. Yt minus 3, again, is simply the linear transformation of the observation at time point yt minus 4 and plus the noise at time point yt minus 3. So I will take that and substitute it for what it is. And if you want to do this, you simply just multiply the black frame this time by a cubed times these expressions will yield the ones that are missing from this representation. Understand what I'm saying? So this is basically what it's going to be. I'm using induction, by the way, so to generalize this. So a cubed times for basically yt minus 3 for what it is. This is basically here, right? And I'm going to do that quick and fill in basically the blank gaps that are missing, because a cube times a constant is a cube times a constant. So you see it there. You have a constant times a cubed. That's that. And then, of course, you do it also for the other expressions. A cubed times a times yt minus 4 equals a to the 4th times yt minus 4. That's that. And then also you have a cubed times the noise at time point t minus 3 equals a cubed times the noise at time point yt minus 3. All right, so this is basically how it is. The third iteration would be basically, you know, that would be the last one, that would be the last one, and then you would have a to the 4th times yt minus 4, as you see. Okay, so this is basically, you know, illustrating how this iteration would, or these iterations would work. I'm going to do another one quick, because I'm going to substitute for yt minus 4, which is a linear transformation of the observation at time point yt minus 5, plus the noise at time point t minus 4. And if you basically multiply those by yt minus, so a to the 4th, then this is going to be a to the 4th times the constant is a to the 4th times a constant. And then you have basically a to the 4th times a times yt minus 5 is a to the 5th times yt minus 5. And then, of course, a to the 4th times the noise at time point t minus 4 is a to the 4th times the noise at time point t minus 4. So this is basically how it evolves. Again, I want to generalize this, so I'm going to look at what the structure would be, but I'm not going to continue. So if you would continue, you would substitute for that, of course, which is here. So, but I don't do this anymore. So that was the last step. Okay, so you put that simply in there, I would continue. But everybody knows what it's going to be, because the fourth iteration, at the fourth iteration, you have the last one is a to the 4th in this bracket, and then you have basically the noise at time point t minus 4 multiplied by a raised by 4, and that's what you have. Okay, so if it's basically the 5th iteration, that would be a to the 5th times the noise at time point t minus 5. If it was a 6th iteration, that would be the final expression would be a to the 6th times the noise at time point t minus 6, and so on and so on and so on. So you know how induction would work. Okay, and what about that one in the middle? Now this is always greater. So if it's the 4th iteration, that is yt minus 5. If it was the 10th iteration, that would be yt minus 11, and so on and so on and so on. So this is basically how it would be. Can I say you up, please? Can you leave the room? Please leave the room. It's not over yet. And close the door. Okay? I don't know. Maybe if she was blind. So at time point t minus 5, this is basically yielding the 4th iteration, and so on and so on. Okay, so that's what it's going to be. And then if it's the nth minus 1 iteration, and n will be basically the number of steps, how far you can go back in time. So if you consider this is going to be the number of steps you can go backwards in time, depending on the time structure. Let's say you go back in time by n steps, okay? Then you will have that for the n minus 1 iteration. So the n minus 1 iteration is going to yield the final expression here for a to raised by n minus 1. And then you have the noise here for the final expression. This is going to be a to the power of n minus 1 times the noise at time point t minus in brackets n minus 1. And then you will have for the process yt would be actually at yt plus t minus n. So again, n is going to be the number of steps that you can go back in time. and you could not go back further. So if t is the current time point, then n is going to be the steps that you can go backwards. Understand what I'm saying? Maybe the process has started at some point somewhere, and that will be basically denoting n. Okay? If n is the number of steps that you come back in time, then you can do n minus 1 iterations max. Okay, so when it comes to these substitutions and whatnot. All right, so that's basically that. Now I want to summarize this. Basically, I'm going to use, to capture those, I'm going to use the geometric series. This is basically a geometric series. I don't know if you've seen this before. But again, if you don't, then it doesn't really matter because there is a formula to this. So simply you can say q to the power of I from I is equal to 0 to m is going to be 1 minus q to the power of m plus 1 divided by 1 minus q. All right, so you've probably seen this formula. Again, I'm not sure. This is the geometric series, by the way, and which it is here. So I'm going to take that, substitute it for it, okay, which is going to look like that, so accordingly. And then I take basically those expressions. I'm going to put that here at the front. And this expression can be expressed by a sum, okay, which is more compact then. So because that all has the same structure. Okay, so here the exponents are increasing, whereas basically the observations, the time points are decreasing. So you have t minus 1, t minus 2, t minus 3, so on. And the common expression is a to the power of j times epsilon at time point t minus j, where j starts at time point 0, or let's say at 0, and then it will stop at n minus 1. So this is basically how we're summarizing it. Yeah?
Why t is dependent on yt minus 1 and 1t?
Because this is the nth minus 1 iteration.
Yes, exactly.
You can now go backwards. So if you have the n minus 1 iteration, then this will be basically the last observation that you can look into.
Yes, yes. But when there are more in the model, right? When there are more y's on the right side.
It doesn't matter. Yeah, that's the only one that basically would depend on in this regard. So if you know what this is, then basically you have just a cumulative sum of these weighted noises again. There is nothing else. Okay, this is basically what the structure of the autoregressive model would be.
But at the end, when there is an error, right, and there is n minus 1, it's a blue color, it should be n minus 2 as well?
No, n minus 1, that's the last.
That's always.
That's the last. Yeah, because at the n minus 1 iteration, if you look into the induction again, so that's basically what it was. If it was the 5th iteration, the last one was a to the power of 5 times the noise at time point t minus 5. If it was the 6th iteration, the last expression would be a to the 6 times the noise at time point t minus 6, and so on. If it was the 10th iteration, then it would be the last expression would be a to the 10th times the noise at time point t minus 10. So if it's the nth minus, I mean, there is no such thing, n minus 1th iteration, but I express it as such. Then n minus 1 is the number of iterations. Okay, so if basically this is the last observation that you can use, then of course you need to do n minus 1 iterations. That's what it is. Okay, so that's why it will stop at time point n minus 1 and not at time point n minus 2. This is what the induction would be. All right, so this is basically, you know, that expression, and this, I was just summarizing it. So this is a representation basically of the first order autoregressive model, basically. And as you see, that includes past observations of noises. And if you look into that, this indicates that the noises, no matter how far they basically are back in time, so these shocks, would always have a direct impact, more or less, on the future observations of the process. Again, so this is basically, no matter how long ago, let's say, the shock has happened, it still has an impact, even if it's tiny, but it still has an impact on basically the current observation of the process itself, and not just the current observation, but even future observations. All right, so because actually, if you just ignore that one, okay, so if you ignore that one, the process itself consists of weighted sums of these shocks. Simple as. And there is a constant related to it. So there's a constant plus the sum of these weighted shocks. That's it, okay? And yeah, so this is what it's going to be. And yeah, so I got 2 minutes left, but this is basically, you know, how the structure would be. And if you allow me to stop here, then I'm going to basically consider or reconsider the next part again, because that involves basically, you know, restructuring time. So next lecture, next week, but this is something that you need to recognize here. This expression can be written as this expression and n will denote the number of steps that you can go backwards in time. So number of steps, basically, how far you can go back in time. Now, how far you can go back in time is depending on the time structure itself, which I'm going to discuss next week. I don't have time for that. I have 1 minute left, so I'm not going to make it. Right?
When the coefficient A is equal to 1, then it doesn't work, right?
It does, because then you have a so-called random walk. Yeah. I'm going to put restrictions on that, but you can use, look, this representation always does work. It does work.
You divide by 0 later.
It doesn't matter. Yeah, okay, this expression does not exist. That's true. But I can overcome this if I say, okay, this constant is 0. Because then it wouldn't be no longer there. Okay? All right? So there is a way to express it, because if it's 0, then you simply would have these sums, okay, of these shocks, okay, which is basically, you know, the integrated version of these shocks, and that is going to be a random walk. So there is but if it's equal to 1, then you're right, you cannot do that directly here, okay, so that's basically true. But in that regard, if I dismiss the constant, there is a way to overcome this, okay, so there is a way to bypass that case, which you mentioned before. So that still includes, okay, you're right, okay, you cannot calculate basically the geometric series, but you don't have to, because the constant is 0 anyway, so you can simply just dismiss that.
In reality, you never really see A equal to 1, right?
Yes, you do. I'm going to discuss that too, but that will be a little bit more complex issue, not now. Okay? So that's going to be a random walk process, which is also a very important class of processes, by the way. Okay? But I'm going to stop here. That's something that you need to remember. You don't need to put that restriction. Of course, you're right. If A is equal to 1, that this expression does not exist, which is true. Okay? But there is a way to bypass that. Okay, so that case. So I would start basically by saying you have a constant plus the past observation plus the noise. And start from there. And if you start from there, resubstituting all the time, you would get kind of similar expression to this one, which is not that important. But it's not important in this case. So it's not basically, you know, important to put restrictions on this matter if you want to transfer this process to that one. Now you might ask, okay, why am I doing that? Because it's uglier than it was before. But I'm going to do it because I want to calculate its moments. That's what it's for. And then we're going to do this next week. Okay, so I'm going to stop here. And then I'm going to continue from here next week. Next Wednesday. There is no assignment this week, except for the current one. So you can relax for a week. And I will keep you informed. All right? All right, guys. That was it for today. Take care. Thanks.